Good morning. I'm Steve Cole from NASA's Office of Communications, and welcome to Kennedy Space Center. We're here today to talk about the first NASA instrument to be launched to the space station to make round-the-clock observations of Earth. That instrument, the ISS-RapidScatometer, or RapidScat, will measure ocean winds. It is headed to the station this weekend aboard the fourth SpaceX Dragon commercial resupply services mission. Today we have here to talk to you about RapidScat three panelists. Steve Volz, Associate Director for Flight Programs at NASA's Earth Science Division at headquarters in Washington. Ernesto Rodriguez, Project Scientist for RapidScat at NASA's Jet Propulsion Laboratory in Pasadena, California. And Howard Eisen, Project Manager for RapidScat, also from JPL in Pasadena. We're really excited about this mission because it will be the third NASA Earth Science launch this year. And we have two more scheduled in the next few months, making this a very busy year with 5 launches in a 12-month period. To get more information about all this activity and a lot of other Earth science that NASA's engaged in this year, please visit this special website, www.nasa.gov/EarthRightNow. We'd like to make this conversation today, so we'll be taking questions throughout the briefing. If you have a question, just raise your hand at any time, and we'll take it and give it to one of our presenters. Okay, we'll get started with Steve Volz. Steve, NASA has 17 Earth-observing satellites in space right now, with more on the drawing board. Tell us a little bit about why NASA studies Earth from space, and what specifically are we observing?
Well, the objective of NASA's Earth Science organization and division is to understand Earth as a system, and really all the different complex intermixed phenomena which are displayed with weather, with solid Earth, with the oceans, etc. And the best way to observe the Earth as an overall system is to look at it from the vantage point of space. The local phenomena that you get from the local weather, the ground systems, can only indicate what's going on in a very small area. But with the global perspective from our polar satellites, from geostationary satellites, such as the weather satellites looking from a fixed point high in space, we get a much better perspective of the overall view of how the different phenomena interact and how the Earth as a system is working. And you mentioned 17 satellites. We do have a significant array of satellites that are in space now. Some of them as old as, I think I was just doing it in my head, in 1997. So they range from 17 to 18 years old to, as you mentioned, 2 that we've already launched just this year. So the array of satellites span multiple measurements, from radar instruments to look at rainfall and clouds, to gravity measurements to look at the movement of Earth, subaquifer Earth under the ocean, under the land, to land imaging such as the Landsat or other image satellites like that, all looking at different phenomena from space.
And what does the space station offer as an Earth observing platform to complement these other satellites?
The space station offers a unique perspective, not necessarily unique, but a very different one from the polar satellites that we have. Our polar orbiting satellites, of which are most of those 17, circle the Earth with high latitude. So we call it sun synchronous, about 98-degree inclination. But they cover the entire Earth. They look at the poles. They look at the center, the equators. But they view a particular spot on the Earth only once or twice at a particular time, only relatively infrequently, like 15, 16-day repeat cycles. So they're limited in their ability to look at the different phenomena at different times of the day. The ISS, the International Space Station, as a platform, flies at a slightly lower altitude, but also at an inclined orbit, which allows it doesn't get to the poles, but it does view the lower latitudes between plus or minus 50 some degrees with a much more frequent time repeat cycle, and also at different times of the day. Our polar satellites tend to look at the particular spot on the Earth at the same time of day when it crosses, whereas the ISS, looking at it in the morning, noon, night, allows us to see the different phenomena as they occur, where you might have weather in the morning, which is persistent in the morning, you wouldn't see with an afternoon satellite, where the ISS can look at all of those. And it complements the polar satellites in that aspect.
And RapidScat is
Oh,
there's a question.
Yeah.
I'm sorry. Yes, go right ahead.
It's kind of a general question.
Sure.
And you're the ideal guy to ask it. Ken Kramer, Universe Today in America Space. The question is, this is such a great idea to use the ISS for Earth science. Why we haven't done this before? And I know you have a program coming up. Can you tell us a little bit about the upcoming plans you have to use the ISS before you go further? Thank you.
Sure. two questions there. Why haven't we used this before, and what are we using it for in the future? So as far as the before part, the ISS is a significant engineering feat that's taken many, many years to put together. And I believe for the bulk of that, up through the 2010, maybe a little later, the focus was on making the facility work, making sure all the parts work together, making sure those same utilities that make it useful as a platform weren't in place, weren't integrated, weren't operating as a system yet. And that period of time it took to do that, and to understand how it's going to operate was really necessary before we as users, science users, know how to utilize it. We understanding questions about just where you can install the instruments, what the microgravity facilities capabilities might be, what the power, what the reliability would be, not in terms of data downlink, et cetera. So the ISS as a platform had to be established, and they spent a long time and a great engineering effort to make that happen. And as that came to fruition, then we started working with, from the science communities, with the ISS program to figure out how to make the most use of it, the best use of it. Now, I actually have an image. You bring up the image of the ISS as a platform. We do have a number of now that we realize the capability of the station, we're taking advantage of it. This picture here that you see shows the ISS-RapidScat, point an arrow to it, and you'll hear a lot more about that from my colleagues here. But we also are looking at in this year, the next one, and we have a CATS, which is a cloud aerosol a LiDAR, which will be flying right around the turn of the year, which will be looking at aerosol products. That's the CATS instrument you see there. SAGE 3, which is actually was designed for the ISS, was meant to launch about 10 years ago, but as I mentioned, the platform wasn't developed yet, so it was deferred, and we put in storage, and now we brought it out, and it's ready, and it'll be launching in 16. That measures the aerosol and the ozone layers. And then we have two others, though the LIS, which is a lightning imaging spectrometer, which will be measuring, which is similar to what we have flying on one of our polar satellites, TRIM, will be measuring lightning. And the last two, I'm going over my time here, but the last two are EcoStress and JEDI. We just selected those two instruments specifically designed for the ISS about 2 months ago. Both of those are looking at land use, land cover, ecosystem, biosystem measurements. EcoStress is a multispectral thermal infrared imager, which complements what we have on our Landsat, but with higher resolution, spatial, and higher spectral resolution. It uses the advantage of the ISS with its diurnal cycle, its variability of its crossing time, so you can look at the thermal stresses on the ground at different times of the day, as well as higher resolution. And the JEDI, which is it's a forest vegetation canopy LiDAR with a great acronym, which is using the lasers to look at forest height. It actually measures the canopy height by looking at reflected light from the top of trees and through all the structure of the trees. It gets multiple returns from each laser pulse, and they can measure the biocontent, the carbon content of the earth, of the vegetation to very high precision. These are capable, the ISS makes them more useful capable for us. The JEDI, for example, lasers take a lot of power and a lot of and that's a lot of facilities, which if I had to build a spacecraft would be much more difficult. The ISS has lots of power and has lots of capacity for that, so it makes it easier for us to design the instrument without having to worry about all the other facilities and infrastructure. So that's just an example of what we have right now on the books, and I don't think that's going to be the end of it because of we just picked these two in this year, and we have regular solicitations and regular opportunities to look for other options. So.
Thanks, Steve. Question for Ernesto. Steve was mentioning all the different Earth system science, the broad view that NASA science, Earth science takes. Could you tell us a little bit about the part of that Earth science that RapidScat will focus on?
Sure, Steve. So RapidScat is going to be looking at oceans over the winds, and you may wonder what oceans over the winds, why are they important? Clearly, there are very dramatic effects like hurricanes, and if you see the graphic that's going to be put up there, this is a graphic of the Hurricane Katrina as it approached New Orleans. What you'll see is that the colors represent the wind speed at the surface. So unlike many optical satellites that can only see the top of the clouds, radar can really get to the bottom and see the speed, the wind speed and direction that affects the people on the ground. So this is a unique capability, and over the last decade, we've had for the first time the ability to monitor hurricanes and tropical cyclones almost on a daily basis. Beyond that, beyond these phenomena, which obviously affect many people on the coast, the winds are a key link for taking all that energy from the sun and transferring it to the oceans. They drive ocean circulation. They also drive the amount of gases that go from the atmosphere into the ocean. For instance, CO2, a lot of it is sequestered in the ocean, and the winds drive that. They also drive ocean productivity, so fisheries and so forth. And the ability to look at these things globally is something really that we've had only over the last decade and a half. Before that, we had to rely on ships giving us very, very sparse data. Nowadays, thanks to scatterometry, we can have a global picture.
You mentioned that the scatterometers have flown in space before. What's needed now to put another scatterometer in place? Why is this important now?
Yeah. So if you look at the image that's coming up right now, it's an animation of the ability of scatterometers to measure global winds. As I mentioned before, this has only happened over the last decade and a half. We've lost the capability due to some losses in the international constellation to do this global monitoring on a daily basis. So the first thing that the ISS-RapidScat will do is help us regain that capability. Together with the EUMETSAT satellite ASCAT and the ISS-RapidScat, we'll be able to go back to daily monitoring. But beyond that, because of the unique capabilities of the ISS orbit, the satellite will observe the other satellites in the constellation on an hourly basis. And this will allow the sort of cross-calibration that ties them all together. We're beginning to understand the circulation of the winds, but the snapshots that we have only span a decade. By tying all these satellites together and transferring the calibration standards from the previous generation to the next generation, we'll really be able to understand climate change over multiple decades, which really is the scale at which it takes place.
And what kind of new science is RapidScat going to be able to let's go to this question, then we'll go to you. What kind of new science will RapidScat be able to endeavor?
So, as I mentioned earlier, it enables the tying in together of the climate picture. But beyond that, because of the orbit of the ISS, it allows it to look at every point on the Earth at every time of day. I mentioned earlier that winds are driven by the sun. Most satellites can only watch the winds at a given time of day, and so we only have a very sparse picture. By looking at the daily cycle, or what's called by the scientists the diurnal cycle, we can begin to understand, as a function of the time of day, how the energy from the ocean through evaporation is going to clouds, and those clouds are precipitating over land, or how evaporation is happening over land as vegetation starts to lose moisture. And so that really is a capability that will be one of a kind, and the first time we were able to do it.
Okay, we have a question in the audience.
Hi, Ken Kramer, Universe Today, America Space again. Yeah, you said this replaces a satellite. So what were the satellites that were lost? And what are the capabilities you're gaining or losing by being on the ISS versus those satellites that were lost earlier?
Okay, so the scatterometer age really started in 1999 with QuickScat. It was a long-lived satellite, lived for 10 years, 5 years over its lifetime, but it has a rotating mechanism, and in 2009 it stopped rotating. So it was still able to serve as a calibration standard, but it was not able to collect wide swaths. Around the same time, the ISRO, which is the Indian Space Agency, launched something called OSCAT on OceanSat-2. That satellite took over from QuickScat, and we used QuickScat to cross-calibrate it, but that satellite died earlier this year. And so right now, there's only a single set of satellites, ASCAT from EUMETSAT, taking data. So by launching at this time and combining the data from ISS-RapidScat and the data from EUMETSAT, we're going back from seeing the atmosphere only once every other day to once every day. So for something like hurricane monitoring, this is a key capability.
I think we'll go over to Howard now. Howard, your job was to build RapidScat at JPL, and I understand that was done in record time and a fraction of the cost of a traditional satellite mission. Tell us about how JPL was able to accomplish that feat.
Sure. Well, RapidScat is the ultimate effort in recycling. We took hardware, some of which was 17, 18 years old, and we put it to new use. If we can take a look at the first video here, you can see some of the instrument hardware in the spacecraft assembly facility at JPL under test. The spinning antenna that you see there puts out about 100 watts, the same as a light bulb, in terms of RF radiation or light, which bounces off the ocean surface and then gets recollected by that antenna and processed through the radar hardware. That spinning mechanism that's there is the original engineering model, which was developed along the way to understanding how the flight model would exist. So we built an engineering model, we tested it, it actually failed some of those tests, we made some changes, moved on to the flight model. We took the engineering model out of storage and we upgraded it. We made some of the same changes we'd made to the flight unit. Some things remain unrepaired, some things were repaired. We did the same thing with the radar electronics. And so by recycling this very valuable hardware, we didn't have to develop all of that new. Instead, we focused our effort on developing hardware which was tying us into the space station, because the space station is a different orbit, a different power system, a different communication system than the satellite we were designed for before. But it was all done with the idea of doing this quickly and cheaply, and the result is we have an instrument that costs about 1/12 what it would cost to do this as a standalone mission right now.
And RapidScat is going to the station with some assembly still required, as I understand it, using the robotic arms on the station. Can you tell us a little bit about how that will be installed and why that kind of assembly was required?
Sure. So we're a target of opportunity here. We were told that there were openings on the space station, and more importantly, there was an opening on this launch vehicle on CRS-4. And so we were told we could do anything we could fit inside CRS-4 in the trunk area, we could put up on station and get our good science done. But the only spots that were available to us weren't facing the Earth, and we're an Earth-looking instrument. So we had to break ourselves into two pieces. We have a video of the installation that shows how this works. So the first thing we do is we go into the Dragon trunk and we pull out this thing called the nadir adapter, nadir meaning pointing towards Earth. And the nadir adapter is just that. It's a right angle bracket that we mount on the Columbus module in an area that normally doesn't face the Earth, and it reorients us so we're looking down towards the Earth. So one side of that has the interface that goes to the station. The other side of it has the interface that normally exists on station. So it looks to the second element, the instrument, just like it. So here's the instrument being pulled out of the Dragon trunk and being translated over to the Columbus module. And this element, the instrument, will attach to the nadir adapter. This is all done robotically. It's all controlled from the ground. The only astronaut interaction we have is they have to flip the power switch on the module to turn our sight off and on. The whole process takes about 2 days. There's one shift involved in putting the nadir adapter on, and then we come back again about 30 hours later and we put the instrument on.
And I think we have a still here to show everybody where that instrument will be on the station. See it right there.
It shows the end of the Columbus module. The Columbus module has 4 external locations for mounting payloads. We're on the one referred to as SDX, which means we face starboard, and you can see with the payload there, our antenna is now facing towards the Earth.
Yes, a question right here.
Associated Press. Are you taking up any spare parts, and if necessary, could a spacewalk fix something?
So it really can't. The payload was never designed originally for any kind of an EVA because it was designed for a free-flowing spacecraft. And so because of that, again, to keep it cheap and as we could, we adapted to standard station interfaces. So for example, we have trouble with the installation itself. We're on the standard interface adapter plates, which are EVA compatible, should there be a robotics problem. But the instrument itself has no EVA provisions.
You mentioned it was supposed to be a free-floating payload. Could you give a little history on that? When was that supposed to happen, and why didn't it?
So this is the engineering model hardware that was developed as part of the Sea-Winds payload, which exists on both the QuickScat spacecraft, the one that Ernesto mentioned, which served us well from 1999 to 2009, and is still in limited operation today. And it was also the Sea-Winds payload was produced on a Japanese spacecraft called Adios 2. Unfortunately, Adios 2 failed shortly into its mission.
We have another question up here.
Yes, this is James Sutton from Spaceflight Insider. Once the power switch is turned on, as you said, how long will it take before this information is going to be distributed, and how do you go about doing that? Like, who gets the information?
Sure. So the station is a very complicated system, and so we can't just plug in and just turn on and be running instantly. In fact, during the week after we get up there, there's a Soyuz launch bringing up a new crew. There's another visiting vehicle coming up shortly thereafter, and we have to interleave ourselves with those operations. But sometime in the first or second week of October, we should be able to turn the payload on. We get data within minutes. Typically, the data comes down via the TDRS network. We get the data ourselves through Marshall Space Flight Center, which does the operations with us. The data comes to JPL, we process it, and then within 3 hours of the data being taken on board, we're able to deliver that data to operational agencies such as NOAA. We'll put out a early product immediately, and then after about 30 days of operation, we'll have that product through a preliminary calibration phase so it can be used by weather forecasters.
Another question in the audience here?
James Dean, Florida Today. Just regarding installation, I'm not sure if I'm remembering this correctly, but is this the first time Dexter will be used to be installing an instrument like this externally?
No, in fact, the last mission, CRS-3, had 2 payloads that were removed from the Dragon trunk and installed on station. Opals and HDEV.
So, I mean, in terms of the risk of that whole process, totally comfortable with that, or was it simulated on the ground, or any concern or anything like that?
Sure, I think we were a little concerned about it until it was successfully demonstrated a few months ago. There are certainly some lessons that were learned in that process. There was a trouble with the grapple the first time through, and I think we've incorporated all those lessons learned, and we feel pretty comfortable. This is the first time, I believe, we're actually attaching 2 payload elements together like this. We've gone and worked with the robotics team at Johnson Space Center, the operations team at Marshall Space Flight Center. We've put additional markings on the payload, additional visual markings to help with the lineups, and we've gone through every precaution we can to try to improve the chance of that working right the first time. We are limited in how much time we can spend attached to the robot arm because the payload cools down. There's no power available to us when we're in the arm, so heaters aren't available, and so we have a 6-hour thermal clock on one part of the element that we need to get installed and get power back up again.
Follow-up question there?
Yeah, I'm sorry. Just what's the planned duration of the mission? Could it go longer than planned?
So again, we're using surplus hardware, so it's kind of hard to determine how reliable it's really going to be. But our intention is we hope to be operating for the 2 years for which we currently have that slot assigned for us. There are other payloads that will follow us onto the Columbus module into that specific location. So it depends a lot on how the manifest changes. But we're hoping for 2 years of operation, which should be enough time for the Indian Space Agency to get up their replacement satellite.
And I'd like to make a comment to follow on to what Howard was just saying. You heard a description of the steps it takes to get the instrument from the SpaceX module onto the station. Those are all very carefully orchestrated, very well choreographed with the ISS. And go back to the question earlier about why haven't we done this before. All of these steps, all of these interactions, all of these dependencies on different features really needed to be understood so that we could design a system that would work. And I'll give an example. We started working on Stage 3 on the ISS about 3 years ago, and it was a surprise to us to realize the toughest thermal environment we'll ever see for the instrument is during that period of time when it goes from the spacecraft and is attached to the station. It's an unpowered period of time. We're not used to that. When we fly our satellites on robotic missions, we have power from the start. We don't have to worry about thermal extremes. We design all of it in so that the environment for an instrument in space is really pretty benign. It's surprising, but it is, because we take care of that with everything else, with the planning and design. Understanding the steps in a space ISS installation, there are a lot of things that are different from how we do on free flyers. They're all surmountable, but they need to be understood and carefully looked at one step at a time. And as we become more familiar with these Dexter and these other robotic mechanisms, the different movements, we can tailor our instruments better, we can make better use of the station. But we need to know that up front so that we design the system 3-4 years before it's just delivered, so that it's not, we don't find a gotchas at the last minute says, you mean I've got to sit there for 2 days? I didn't think about that, or I got to have another marker here. These are the kind of details that really take time and practice and experience to understand. And as each of these, a lot of firsts that Howard mentioned, there are going to be a lot of firsts on CATS when we go on the GEM-EF, the Japanese Experiment Module. Each of those sets the path for an easier transition for the next instruments we want to fly in the same way.
Another question up here in the front. Just wait for the microphone.
Matt Coons from the social media. Do you have any predictions as to how much this will potentially increase the accuracy of the NOAA weather forecasts long term?
Yeah, there are many different types of weather forecasts. You know, there are forecasts for hurricanes, there are numerical weather prediction forecasts. Right now, I think that the biggest impact that it will have is this ability to close the gap on seeing things that change quickly, like hurricanes. Right now, it can happen, and it does happen, that the ASCAT scatterometer will completely miss a hurricane as this is intensifying. By having an additional platform that helps bridge that gap, we will have at least daily observations of hurricanes. Now, this is especially important not as it approaches land, where we have airborne facilities, but when it's forming and when it's actually starting to move, predicting things like where it's going to go from Africa all the way to America is really hard with our satellites, and having that daily observation really, really helps.
Any other questions in the audience? Yes, right here in the middle, if you could wait for the microphone.
So I noticed that the space station's docking ports are within the field of view for your device. So how much of the field of view do you lose, and will this affect your measurements overall?
So we actually don't see the docking port itself. We do see visiting vehicles when they're located there. And although, as I said, we're only putting out 100 watts, there is a concern that we are inducing that electromagnetic field on the visiting vehicles or on other things that are in the area. So one of the things that we did when we designed this payload is every time it spins through its 360-degree arc, it actually shuts down. We actually take the signal that's going into the radar and we shunt it. We drop it into a load for about 1/6 of the rotation. And so we don't spray that signal over the visiting vehicles or over the docking ports. It turns out that because of the direction that we fly and the way it works, we only lose about 4% of our swath width in that case. So we have a 500-mile wide swath. That's just cut down by a little tiny bit.
Thank you. Any other questions? One more back with James Dean.
Sorry, not to look too far ahead, but end of mission then? Are you going to just kind of chuck these things overboard, or will they be tucked in a Cygnus or something like that, or what happens when you have to
the payload
replace
comes
it?
up on a Dragon, it goes down on a Dragon. So the Dragon trunk section has what's called the cargo rack in it, which is what we tie to, and we are robotically removed at the end of mission as two pieces, put back in a Dragon trunk, and the Dragon ejects the trunk on reentry, so we will burn up. And I'll tell you, I'd much rather have this hardware after 19 years at that point burn up than just sit in a warehouse.
First question.
And Associated Press, is data collected all the time? I mean, is it continuous? Is that your plan?
That's right. We collect data continuously 24/7. And then in the post-processing, we know when we're over land. We know when a solar array may have come into our field of view. We know when we're shut down because there's an EVA going on or things like that. And so all that goes into the processing stream, and it's all taken out.
So like during the spacewalk, you would shut down?
If the crew is coming into our local area, we have a keep-out zone. Same thing. If they're in that zone where they're likely to be within the field of view of our antenna, we will shut down for that time period.
And is that their safety, or is it instrument safety? Or
It's all for their safety. We have lots of precautions in place for astronaut safety.
So just to clarify, like this team worked on QuickScat as well?
In fact, many of the team members worked on QuickScat, and if they weren't available to work on our team now, we at least brought them in as consultants and reviewers. Many of the science team members have been with us for quite a long time.
In fact, the space age scatterometry and measurement of winds started in 1978 approximately. We have team members dating all the way back from then, so we really have a very veteran team, unfortunately.
What has changed in scatterometer technology over 10 years when compared to like a decade ago?
So as Howard mentioned, we're really using the same hardware over again. It worked really, really well before. Of course, we have long-term vision of how things should go in the future, higher resolution and so forth. But for the moment, it really is important to keep this observational capability going on. So we need to observe things on a daily basis. We need to be able to cross-calibrate. And so this is the best hardware to do that.
Another question? Ken?
Hi, Ken Kramer, America Space. You mentioned that Right, this is on Columbus, which is a European module. Does that involve barter agreements where we have to give them time on a U.S. Area at all?
I don't know what agreements we have with them with respect to that. I know that we have worked very closely with them on integrating this payload. They've signed off on all of our interfaces and such, and all of our tests and verifications and things. They're an integral part of our team. I don't know what larger agreements the station program has.
And you are limited to 2 years, is that right?
We are limited, well, we're up there until we're scheduled for replacement. There has to be the right mix of the new payloads coming up and the right Dragon opportunity to take us down. There has to be an opening in the trunk. So it's it's at least 2 years. How much longer depends on the manifest.
And if ESA wants to put something in that spot, could you move it to another spot on the ISS if there was an opening?
So we haven't today certified ourselves for another spot. That might be possible, but we've particularly looked at things like trying to avoid radiating the visiting vehicles and things like that. So it would be difficult. The next payload that is coming up in that spot is an ESA payload, and on the manifest it is 2 years out.
There are a number, I think it's on the order of 25 external attachment points, and some of those may be multiple. You could have multiple instruments on one attachment point on the ISS. And I think the ISS is now getting to the point where they are starting to fill it up. That doesn't mean that we shut the doors and nobody else can apply, because we want to make best use of the ISS as a platform. So when some satellite instruments or measurements are old or aging or sort of diminishing return because they've failed a little bit or parts of it are not working as well, there's a whole manifest review process and a process by which the Science Directorate and the ISS works with many organizations, but specifically with the Science Directorate looking at the prioritizations of individual measurements, the future utilization of the station as a whole, and we make manifest decisions looking well down the road. Which led, for example, to the decision to manifest both the EcoStress and JEDI on the GEM-EF payloads, which is the Japanese experiment module, but it's a multi-use facility that any of the partners have access to, but with different bartering arrangements, as Howard mentioned. But so the spreadsheet of the accommodations is much more busy than a hotel seating chart, room chart. There's lots of people who want to get in, and there's lots of different capabilities that are tailored to different spots. It's a fairly complex but well thought out process as we try and fill up all the slots with the best science.
Okay, any other questions? If not, okay, I'll remind everybody that we have a lot more information online about this mission and the upcoming Earth Science missions. It's at the website www.nasa.gov/earthrightnow. We have 2 more briefings coming up this morning on other scientific research and technology projects launching on the SpaceX Dragon this weekend. The next briefing will begin at 10 o'clock Eastern, and our third briefing today begins at 11 a.m. Eastern. Thank you for watching.